Good morning.
Good morning, sir.
Okay, so today we are going to look at one very beautiful thing of mathematics known as Hadamard matrix. And from this Hadamard matrix, we will construct another beautiful thing known as Golay code. Golay code is a perfect code. And so I'll give you the construction of binary Golay code first, and then we'll talk about the ternary Golay code. Okay, so this is really very, very interesting topic. So we start with Hadamard matrix. Now, before I start this topic, let me show you one famous lady known as Hadamard Matrix lady. Professor Jennifer Sabri. She's a mathematician in Australia. She is known as Hadamard Matrix lady, mother of cryptology in Australia, the grandmother of computer security. She has done tremendous work on Hadamard matrix, and Hadamard matrices are very useful in communication, cryptography, security. So this is a very interesting topic. So what is the Hadamard matrix? So Hadamard matrix is a matrix of size n by n. I can say that n by n, with inside entries either +1 or -1, +1 or -1, such that H transpose is equal to Ni. This is the definition of the Hadamard matrix. So it's a square matrix of size n by n with entries +-1 such that H transpose is equal to Ni. Now, what is the meaning of this condition? This condition means that if you pick up an ith row in this matrix and the jth row in this matrix, so their inner product will be 0, provided I is not equal to j. If you take any two distinct rows, okay, so rows are orthogonal in this matrix. Also, one can show that columns are also orthogonal, that ci and cj is equal to 0 if I is not equal to j. Rows are orthogonal and columns are orthogonal. These are some very basic properties of Hadamard matrix. We call a Hadamard matrix to be normalized if is all one vector. Okay, and first column is also all one vector. If first row or first column is all one vector, then we say that the matrix is normalized. Now let us take some examples here now. N is equal to 1. What is the Hadamard matrix? It turns out that H1 is equal to single 1. Okay, so this is your 1 by 1 Hadamard matrix, trivial matrix. N is equal to 2. H2 is 1, 1, 1, -1. Now you can see that this is a 2 cross 2 matrix, and rows are orthogonal and columns are orthogonal, and this is normalized Hadamard matrix, right? The first row is all 1, first column is all 1. Next example, for n is equal to 4. So the matrix is nothing but 1, 1, 1, -1, 1, 1, 1, -1, 1, 1, 1, -1, -1, -1, minus 1, 1. Okay, this is your 4 cross 4 Hadamard matrix. You can, again, this is a normalized matrix because all one vector is the first row is all one vector, first column is an all one vector. Okay, so the question is, how do we construct such matrices? There are different constructions known in the literature, and there are many good, interesting books which you can find on Hadamard matrices. Okay, actually, you can see that here. The size of the matrix is 1. Okay, here it is 1 cross 1. So matrix exists for n is equal to 1, n is equal to 2, n is equal to 4. Can I say that there is a Hadamard matrix of order 5? So probably not, right? So when there is a Hadamard matrix, so that theorem is summarized here. If a Hadamard matrix of order n exists, then n is 1, or then n is 1, comma 2, or n is multiple of 4. Okay, so if a Hadamard matrix of order n exists, then either n is, so n is either 1, 2, or a multiple of 4. This is a very interesting result. So let us see this proof. Proof is not very difficult here.
So, sir, for n equal to 6, we can't generate the matrix.
Yes, we cannot.
Okay.
So if a Hadamard matrix, so basically the proof actually goes like this, that I'm going to assume that without loss of, without loss of generality, suppose H is normalized. Suppose H is normalized. We are looking at normalized matrix. That means the first row and first column is 1, all one vector. And suppose n is greater than or equal to 3. I am excluding the case 1 or 2. I am assuming that n is greater than 3 because those are the trivial cases. Suppose the first row is 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. The first row is all one vector, right? Without any problem. Second row, we can say that all one, then minus, 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 minus 1, minus 1, minus 1, minus 1, minus 1. Okay. And third row, all one, minus 1, minus 1, minus 1, all one, minus 1, minus 1, minus 1. Suppose we know the first three rows are like this. We have taken plus 1 and minus 1 because we know that some of them will be plus 1, some of them will be minus 1. Suppose that these are I entries, these are j entries, and these are k entries, and these are l entries, right? So from this, since the rows are orthogonal, we will arrive at these we will arrive at these conditions, that I plus j minus k minus l is equal to 0, right? Because when you take the inner product, I plus j minus k minus l is equal to 0. Other rows are orthogonal, so we will arrive at I minus j plus k minus l is equal to 0. And third one will be I minus j minus k plus l is equal to 0. Solving all these equations, we will arrive at that I is equal to j is equal to k is equal to l. This implies that, you know, n is multiple of 4 for I or 4k, whatever you say, right? So this is a nice simple result. So if a Hadamard matrix of order n exists, then n is either 1, 2 or a multiple of 4. Okay. So this is a small result. Now this says that if a Hadamard matrix of order n exists, then n is 1, 2 or multiple of 4. Reverse is still an open problem. Okay. So Hadamard matrix exists whenever order is a multiple of 4. That is not known. So if a Hadamard matrix of order n exists, then n is 1, 2 or n multiple of 4. But if n is a multiple of 4, whether there exists a Hadamard matrix of order of that order, that we don't know. Okay, so the reverse does not true. Okay, this is very important thing. Let me. So this is there is a conjecture now. And conjecture says that Hadamard matrix exists whenever order is a multiple of 4. No proof is known yet. Okay. So this is an open problem. Interesting problem. Okay, so these are the two basic results about the Hadamard matrix. Now I am going to give you one construction, one very nice construction known as Sylvester construction. Okay. Construction 1. So this construction says that if Hn is a Hadamard matrix of order n, then H2n is also a Hadamard matrix and the order is 2n, which is Hn tensor product H2. I'm going to explain to you what is tensor product. So in other words, this is Hn, Hn, Hn minus Hn. Remember H2 was what? H2 was 1, 1, 1 minus 1. So basically we have blown the entire H2, okay? So let us, so basically, from H2 you can construct H4. I think if you look at here, H2 is from this side. So, this is your H2, H2, H2 minus H2. You're blowing from this side, taking tensor product from this side. I think this is a very basic thing. Construct. So from here you can construct H2, H4, H8 and so on. Okay. Now, Now I'm going to describe another construction which is known as Paleo type construction, and this involves looking at a beautiful thing. So basically, in mathematics, most beautiful thing is number theory, and in number theory, there is a most beautiful thing known as quadratic residues. I'm going to talk about quadratic residues, and then I will show you how quadratic residues can be used to construct these Hadamard matrices. So something beautiful, and from that you can construct another beautiful thing. So quadratic residues. Okay. So suppose P is an odd prime. P is a prime number. P is not even, but P is a prime number. We look at non-zero square squares modulo P. That is, we look at the following numbers: 1 square, 2 square, 3 square, everything modulo P. So, okay. So these things are known as quadratic residues mod P. I'm writing shorthand, quadratic residues mod P. Now, since P minus A whole square is same thing as minus A whole square, same thing as A square mod P. Okay. So we only consider up to 1 square, 2 square, P minus 1 by 2 whole square. We only go up to half because they start repeating. So let me show you an example and it will be clear to you. Let us take P is equal to 5. Okay. So 1 square is 1. 2 square is 4. Now if you take 3 square, so I am taking everything modulo 5, right? 3 square is 9. Modulo 5 is 4. And then 4 square is 16. Modulo 5 is 1. Right. So these are repetitions. So we have to go only half of them. So that means quadratic residue set is 1 and 4. And quadratic non-residue set is, 2 and 3. They are quadratic non-residues. Okay. Let us take another example. P is equal to 11. So you can see that quadratic residue set is 1, 3, 4, 5, 9. And quadratic non-residue set 2, 6, 7, 8, and 10. Okay. So this is true because you can compute the square and see, 1 square is 1, 2 square is 4, 3 square is 9, 4 square is 5, modulo 11. Everything we are doing modulo 11, right? So we get 1, 3, 4, 5, 9. Okay. 5 square will be 3 actually. So these are quadratic residue and quadratic non-residue. Now there are certain properties of these things. So properties are, first, a quartic residue into quartic residue is again a quartic residue. The product of two quartic residues will give you quartic residues. So for example, here 1 into 4 is 4, which is a quartic residues. Here if you can take 3 into 4, 3 into 4 is 12, modulo 11 is 1, which is a quartic residue. If you take two quartic residues and if you compute their product, you will get quartic residues. Okay. If you take two quadratic non-residue and multiply them, you will again get quadratic residues. Okay. And if you take one quadratic residue and one quadratic non-residue, you will get quadratic non-residue. These are some very basic properties. Okay. Another property, second property I am going to talk about. If P is of the form 4k plus 1, if your prime can be written as 4k plus 1, then minus 1 is a quadratic residue mod P. And if P can be written as 4k plus 3, then minus 1 is quadratic non-residue mod P. So the minus 1, that is P minus 1 modulo P, is quadratic residue or quadratic non-residue depending upon the form of the prime. 4k plus 1 means like 5 is like 4k plus 1, right? 7 is like 4k plus 3. Okay. K, you can take 1, 2, 3, 4, so on. So this is a very basic property about telling about when minus 1, that is P minus 1, is quadratic residue or quadratic non-residue. Now, third, if again P is same thing, a prime number, odd prime, we define what is known as Leandre symbol. Okay, and it's kind of a characteristic function. Chi of I is 0 if I is a multiple of P. Okay, this value is 1 if I mod P is quadratic residue and is minus 1 if I mod P is quadratic non-residue. So this is a function which characterizes whether a particular integer is quadratic residue or quadratic non-residue, right? Okay, so from this construction, from this function, we construct what is known as Hadamard matrix. How do we do this? It's a matrix of size P cross P. Entries are Qij. It's a P cross P matrix where Qij is nothing but characteristic of J minus I. That Leandre symbol of J minus I, right? So let me try to write down this matrix for P is equal to 7 for you. Okay, 0, 1, 2, 3, 4, 5, 6. Here 0, 1, 2, 3, 4, 5, 6. So we need to adjust a little bit. Okay. So the first entry is 0. Second entry is 1 is a quadratic residue. 2 is a quadratic residue. 3 is a quadratic non-residue, so -1. 4 is quadratic residue. 5 is quadratic non-residue, quadratic non-residue. Right? Then minus 0, 1, 1, -1, 1, -1. Okay? Here it is minus, -1, 0, 1, 1, -1, 1. Right? So this is how you can construct it completely. I'll just write down few lines here. 1, 1, -1, 1, -1, -1, 0. Okay, so rest of things I am not filling it. You can fill it as an exercise. So this is known as Jacob's matrix. For p is equal to 7, we have constructed it. You can note down that in this case as chi of j minus I, which is same thing as chi of -1, chi of I minus j, same thing as minus of q of ij. Sorry. Ji. Okay. The Hadamard matrix construction can be constructed like this. H is 1, all one vector transpose basically, and q minus I. One can show that H transpose is equal to P plus 1 times IP. Okay, so this is known as normalized Hadamard matrix of size P plus 1 cross P plus 1. So this is a way to construct the Hadamard matrix known as Paleo type construction. Okay. Now I am ready to describe to you what is known as Golay code construction. I am going to construct the extended Golay code. The parameters are 24, 12, and 8. Okay, and then the punctured code of it is nothing but the perfect code. So that is 23, 11, 7. Okay. So how do we construct this 24, 12, 8 code? So we construct a generator matrix like this. There is a infinity 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Again infinity 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the indexing. So let us construct the matrix. Okay. So here will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So first column is all 1, and then there is the last bit is 0. Okay, so here we have so this is all 0, this is 1, 1, 1, 1, 1, last 1. This is kind of identity block. Okay. Now, so this is 12 cross 24. 12 rows, 24 columns. So you can see that here this is all 1, then there is 0. Wherever I have not written anything, it's all blank 0. Okay. This is all 0. Now, this portion we need to fill. So this is a Jacobstal kind of matrix or Paleo type construction if we use. So this will be 1 is a quadratic residue, so we'll put 1. 2 is a quadratic residue, we'll put 2 is a non-quadratic residue, so we'll put 0, of course. And 3 is a quadratic residue, so 1. 4 is a quadratic residue, 5 is a quadratic residue, and then 9 is a quadratic residue. Rest of the all places it is 0. Okay. Next you can see that it is 1, 1, 0, 1, 1, 1, and all 1. So essentially all these rows are kind of cyclic shift. And the same thing was observed in Jacobstal matrix. You can see here that the first row is 0, 1, 1, minus 1, 1, minus 1, minus 1. Then there is a shift minus 1, 0, 1, 1, minus 1, 1, minus 1, right? So these rows are shift, cyclic shift. Okay. So this is how we construct the matrix. So whenever there is a quadratic residue, we put 1 and otherwise 0. And at the place of 0, we are going to put 1. Okay. So first of all, you need to make sure that all these rows are linearly independent. Okay. So that the dimension is 12 for this code, which is clear because there is an identity block here. You see that, this because of the structure of the matrix 1, 1, 1, 1, 1 in the diagonal up till this place. So all these 12 rows are linearly independent. So the dimension of the code is 12. Length is 24. Okay. Now, so we can say that length of the code is 24. Dimension is 12 because of the identity block, because I12 is sitting here, right? Now, what about minimum distance? Now you can see that right hand side portion, the weight is 6, right? For the first row has weight 6 here. Second row has weight 6. If you take combination of them, if you just take addition of any two rows, for example, if you take first and second row, the weight is 1, 2, 3, 4, 5, 6. So even if you take combination of in rows, any number of rows, you get weight 6. Okay. So 6 weight is from this. Okay. 1 is from this side because these are 11 ones here and 1 from here. Okay. So basically, ultimately you are going to get weight is 8. Okay. So 8 weight vector is there. So you can do the analysis actually and make sure that the minimum distance is 8 of this code. Okay. So all that analysis I leave it to you. Now there are certain properties which I will mention. I think many of them without proof. The first one, So we can denote the code by G24. G24 is self-dual code. So G24 is same thing as G24 per. Very basic property, very important property. This code is G24. By the way, in Voyager 1 and 2 spacecraft in 1977, Golay code was used. Second property, weight of every code word of Golay code is multiple of 4. Okay. Third, G24 contains all one vector. This is clear, when we add everything here, we will get, all one. Fourth property is really interesting. I think we can go to the next place. Yes, fourth property. If C is a code word with left block and right block, okay, something like A infinity, A0, A1, A10, then B infinity, and so on, B10. Then we also have, if this belongs to G24, this will imply that, we have swap code word. Swap code word is also like L, B infinity, B0, B10, A infinity, A10. This also belongs to G24. So this is a beautiful symmetry. Okay, if something like this is there in the code word, it's swap coordinates. We are just swapping half block. That is also okay. Fifth property. So if left block has weight, if C is left and right, belongs to G24, such that weight of L is I and weight of right block is J, then there exist L prime and R prime in G24 such that weight of L prime is J, weight of R prime is I. Okay, this is also interesting thing. Now possible weights are multiple of 4, multiple of 4 means 0, 4, 8, 12, 16, 20, 24. Okay, now we'll see that there is no code word of weight 4. Okay, and if there is no code word of weight 4, because of all one vector, there is no code word of weight 20 as well. You know, we don't have any code word of weight 20 as well. That's our sixth property. No code word weight 4. Because of all one vector, this implies no code word of weight 20. Okay, so from here you know that if AI denotes number of code words of weight I, so A0 there is only one code word, same thing as A24. Okay, and A8 is same thing as A16. So we have the possible weight distribution. I is equal to 0, 8, 12, 16, 24, and AI 1, 7, 59, 2, 5, 7, 6, 7, 5, 9, 1, 7, 5, 9, and 1. Okay, so we can actually just delete the last column. If you want to go for the binary perfect code, binary perfect Golay code, we just delete the last column. So we get a generator matrix G23, I12, and then A hat. So we get a code, parameters 23, 12, 7. Similarly, so this is a binary Golay code, which is a perfect code. So please verify that this is a perfect code. Okay. Finally, I can also talk about ternary Golay code. Its generator matrix is I6 and some matrix B, where B is the following matrix 0, 1, 1, 1, 1, 0, 1, 2, 2, 1, 1, 1, 0, 1, 2, 2, 1, 2, 1, 0, 1, 2, 1, 2, 2, 1, 0, 1, 1, 1, 2, 2, 1, 0. So this gives extended Golay code 1266 ternary Golay code, and the punctured one will be 1165, which is perfect. Okay. So I think that's all for today. We talked about Golay code, its construction. Next class, we will look at the Reed-Muller code, and then we'll go to the cyclic code. Thank you.